Once he gets put that, then we'll turn it over to you, Pat.
Thank you very much. I think the sound should be coming on. I'm Patrick Longmire, and I'm a member of the DOE Oversight Bureau in Los Alamos. I just want to give a 2-minute summary of my experience. My master's and PhD is in groundwater geochemistry, and I've worked at Los Alamos for 21 years and led a lot of the efforts in determining background water chemistry, background soil chemistry, as well as site characterization. And I'll never forget this date. On December 20th, 2005, I briefed upper management at Los Alamos on the chromium contamination. And part of my routine job was to look at the groundwater data and make an assessment. And so I was involved with the team up to about 2 years ago, quite a bit with designing the characterization studies, looking at the drilling of the wells, and defining how is the aquifer system responding to the chromium contamination. And part of the Oversight Bureau is we work with Los Alamos and with DOE and with the Hazardous Waste Bureau. So it's kind of a unique position where we can provide an independent evaluation and try to bridge the gaps in certain areas. So this afternoon, what we'll do is look at some of the sources of the chromium, how it migrated to the regional aquifer, what's the distributions, how is the system responding to this, and then look at what can we do about it. Okay, so I've talked to Justin Marvel, a good friend of mine who's at DOE headquarters. He's a hydrologist. And the chromium contamination at Los Alamos is one of the most significant contaminant issues within the DOE complex, mainly because there's 1,000 feet to the regional water table, and the complexity. Water flows through fractures, it flows through a porous media like a sandbox, and just defining the pathways, and then the issues with remediation where you have contamination 1,000 feet below the ground surface. So in this presentation, we'll look at the, get my little laser pointer. We'll look at just a summary of the chromium contamination, the sources. Then we'll look at some of the groundwater hydrology, some of the aspects of that within the regional aquifer. And then we will look at the concentrations of, see, I'm trying to find it. There we go. We will look at the chromium distribution within the regional aquifer, how fast is it moving within the regional aquifer, and then natural attenuation. This deals with the physical, chemical, biological properties of the aquifer material in reducing the concentration, the mass, and the volume of the contamination. Then we'll look at several remediation options and then provide a summary and conclusion. So here's a view to the west of Los Alamos, the Sierra de los Valles and the Jemez Mountains, and here's the town site. The laboratory is part of the laboratories here. The main source of the chromium was at the technical area 3, the cooling tower, that had discharged from about 1956 to 1972 between 32,000 and 71,000 kilograms of potassium dichromate. There was another source of chromium at TA2, the Omega reactor, where Enrico Fermi was working on plutonium chemistry, and then another source at TA48. And TA48, that canyon, that's part of Morndad Canyon, and so part of the chromium that was released was entered into that canyon. Okay, so over 15 years of chromium releases from technical area 3, the cooling tower, and the potassium dichromate was mainly added as an anti-corrosion agent. There was also dilute solutions of sulfuric acid to adjust the pH, so the chromate would coat the iron surfaces to prevent corrosion. And between 31,000 and 72,000 kilograms of chromate with a mean of 54,000 kilograms were released between 1956 and 1972. And the main form of this was as potassium dichromate, which is a very soluble compound. It immediately, as it breaks apart or dissociates, forms a negatively charged molecule that under the conditions, surface water conditions and the hydrology conditions, can move with groundwater. So the laboratory had estimated approximately 1,100 kilograms of chromate reached the regional water table. This was based on the drilling of 2 other wells that showed contamination, R50, which has about 100 micrograms per liter, 100 parts per billion chromium, and R62 that has approximately 100 to 200 micrograms per liter chromium. So what we need to do is, and this is expected, as you get more information, we'll fine-tune what the mass is of chromium in the subsurface.
Pat, is it all chromium 6 that you're picking up there in those 2 wells?
Yes.
Okay.
Yes, it's chromium 6. Yeah.
So, get it in perspective, you're looking, how much it really is, 2.2 pounds per kilogram. So if you want to multiply that basically by 2, that's how many pounds was actually released in the environment. That helps put it in perspective.
Right.
And Pat, how was that calculated? Was there an assumed concentration for so many gallons of water discharged?
So what Kate Birdsell did, she did a very thorough evaluation going back through the records at the TA3 cooling tower, looked at their daily amounts of chromate, potassium dichromate that was added. And what we did, where we had access, is drilled a series of core holes down maybe 100, 200 feet in Sandia Canyon, and then looked at the amount of residual chromate that was tied up, in the geologic strata in Sandia Canyon. Tried to estimate the amount of chromate. There's a wetland in Sandia Canyon, and that's good news because that is sequestering a lot of the chromium in that wetland. And then where the biggest uncertainty is, it comes into the nature and extent. Because of when R62 was drilled, it was anticipated that was going to be a background well that might show between 3 and 5 parts per billion chromate. It ended up showing 100 to 200 parts per billion chromate. So where there's an uncertainty is where exactly are all the places, what the lab has called drip points, where this chromate is actually entering the regional aquifer. And that needs to be determined in order to do the mass balance and determine more precisely the numbers. And that information only comes with the drilling of more core holes or wells. We can try to model that, but it's a complex system. There's fracture flow and there's porous media flow. Okay, so here is a water table map for the regional aquifer, and this is analogous to a topographic map. Groundwater generally in this portion of the laboratory, here's the laboratory boundary. Morton Dead Canyon is in this area here. The groundwater flow is generally to the south-southeast. And based on the characterization efforts that Los Alamos conducted on pumping tests at a well R28, which contains about 400 parts per billion chromate, the flow rate, the groundwater flow rate ranges, or is estimated to range between 73 and 164 feet per year. Now, this is where it gets complicated hydrologically. The contours tend to spread out. So to determine, and it's a very flat surface, is the groundwater flowing, is it continuing to the east or to the southeast? And this happens to be right in the area of the centroid or the highest concentrations of the chromium contamination. So the hydrology is key because we're dealing with a contaminant that does not attach to the rock surfaces or the minerals at the pHs between 7.5 and 8.3. So the hydrology is going to have a lot of influence on how this plume is migrating.
Where's the background one?
And so we have a series. I'll show another photograph where we have our background data. But the New Mexico Environment Department has gone out and collected 102 samples from about 30 different background stations, and I'll show that very shortly.
What are the scale lines that we're looking at? Is that 1,000 feet, or is that surface? What exactly are the scale lines?
Okay, so what I've provided with the computer on the laptop here is a handout of the, I'm going to have to go up and look at this contour interval here. I believe we are looking at about 2 feet contour, so that the elevation of the water table decreases to the east, southeast, and it's a 2-foot contour interval between this.
Pat, is that border the Rio Grande?
So the Rio Grande, yes, this is the Rio Grande here with several springs that discharge along the Rio Grande.
What is the distance from where the arrows are to the Rio Grande?
Okay, that's probably on the order of about 3 to 4 miles. And if anybody has more precise information, I'd gladly accept that. Okay, so with that, here is a map showing our background concentrations, and this is New Mexico Environment Department data, 102 samples collected from about 32 stations, and we based our criteria on background is that background chloride concentrations in the regional aquifer are about 2 milligrams per liter or 2 parts per million. Chloride moves at the same rate as groundwater. And then we also looked at tritium. There is natural tritium that's produced in the atmosphere. That's about maybe between 10 and 20 picocuries per liter. And there's contaminant tritium that's been released from the laboratory. We had another criteria that if the water samples we collected from these locations did not detect tritium at less than 1 picocurie per liter, we deemed that to be background, that it was not impacted from laboratory discharges commencing in the early 1940s. So we also use high-resolution mass spectrometry. This is an EPA method, but the detection limit, and this is a typo here, our minimum detection limit is 0.05 micrograms per liter. And when I worked in the ER project, I took detection limits very seriously with our data. We wanted to have basically where we could detect a contaminant if it was there or not. The laboratory has excellent contract labs to look at chromium and other contaminants, but our detection limit is about 2 orders of magnitude lower than what the laboratory has provided on their sampling for their analyses. So with this, our ranges are about from about 2 to about 5.7 micrograms per liter for our background chromium. And this shows the wells, the location. Morton Dead Canyon is right here, and we also went to other wells within the area that we had also a lot of data. We had sampled the White Rock Canyon Springs, and so this provides a fairly robust data set for background concentration. We also looked at other metals, but for this discussion, we're interested in chromium. Now, to make a regulatory decision, our mean background concentration of chromium is 3.12 plus or minus 1 microgram per liter. Our upper tolerance limit is 5.2 micrograms per liter. So that just tells us if you had a well and you detected 15 micrograms per liter of chromium, there potentially could be an anthropogenic component because it exceeds background. Okay, now the New Mexico Water Quality Control Commission standard for total chromium, that includes chromium 3 plus chromium 6 plus, is 50 micrograms per liter, and the EPA has a standard of 100 micrograms per liter. Okay, so that's what we know right now about background chromium. And here is a map showing the chromium plume as defined at 50 micrograms per liter, or the New Mexico Water Quality Control Commission standard. And so as the laboratory has talked about, R42, R28 are some of the key wells, where at R28 the concentrations typically range between 350 and 400 micrograms per liter. At R42, the concentrations can range from about 900 up to about 1,250 micrograms per liter, with more common values at about 1,000 micrograms per liter. So here is R50 that was drilled about 360 feet north of the laboratory boundary, and right now that well contains about 100 micrograms per liter of chromium. And then here is R62 that contains between 100 and 200 micrograms per liter. So some of the key questions in our conceptual model on the distribution of chromium in the regional aquifer is, we know that it's entering at probably entering near R42, and there can be flow to R28, but there also can be flow to R50. And the laboratory discussed this in their 2012 report based on, I think, some fairly rigorous, competent hydrologic modeling. So there has to be a drip point near R62, and so to determine the mass and the total volume of chromium in the regional aquifer, we need to define background within the Morton-Dad-Sandia Canyon watershed. Okay, there's this well R1 that has about 5.1 micrograms per liter, pretty close to our UTL, but that well is contaminated with nickel. Background nickel is about 1 or 2 micrograms per liter. This well has above 10 micrograms per liter. So there's some uncertainty. Now, what we feel is important, and I know the lab feels this with my colleagues there, is that if we're going to, the best way to clean up this aquifer, the regional aquifer, is we need to define the complete extent of contamination on site and the potential movement south of R50. And again, the laboratory had determined through hydrologic modeling that west of R42 and R28, the plume generally is migrating 20 degrees south of east, and then south of R42 and R28, about 65 degrees south of east. And this could be controlled by paleo channels, you know, where the water's moving at a greater ease. Now, the laboratory and the Oversight Bureau, we monitor the supply wells, and we split samples, and we go out and sample. Yes?
I want to understand R42 and R62 a little better.
Okay.
You said R42 is like on average 1,000?
Yes.
And R62 about 200?
100 to 200.
100 to 200. But the migration direction is generally south to southeast. R62 being north.
Right.
West.
So
you call that a drip point, but the original entry point is R42?
this could be.
That's got an independent
This would be an independent, probably.
Okay.
And so because of the high concentrations near R42, we are probably, where this well was drilled, is fairly close to most likely a drip point. There also is this well, R43, that the concentrations when this well was drilled in 2009 or 2010, it was near background. It was about 3 or 4 micrograms per liter. Now it's at 56 micrograms per liter. So,
Before you go on, I'm not understanding your numbers, is this chromium 6?
This is largely chromium 6.
Okay, the standards you mentioned are total chromium.
Our total chromium.
Okay, so we're not, I mean, this could be way above the total chromium standard and even further above hexavalent chromium standard if there is one ever developed.
Right. The state of California is probably going to adopt a standard of 10 micrograms per liter for hexavalent chromium. They have, some people have proposed 70 nanograms per liter hexavalent chromium, but there is natural chromium that's in California and the western United States that's even higher than that. We went out, when we had delineated this contamination in December of 2005, in the early part, mid part of 2006, we went out and analyzed specifically for hexavalent chromium. And I could say as a rough rule of thumb, over 95% of the total chromium that we've measured in these wells is stable as hexavalent chromium, as chromium.
I just wanted to get an idea of what we were comparing it to.
Right. And the standard is just based on the total chromium as 50 for the state standard and 100 for the EPA standard. But all the toxicity is pretty much due to the hexavalent chromium. So we monitor the supply wells. There's PM3, PM4, PM standing for Pajarito Mesa, and PM5. Now, so this shows at PM5 about 5.3 micrograms per liter, PM4 about 6.2, 5.6, PM3 is about 3 micrograms per liter. What the laboratory realizes and what we realize is that PM4 is pumping now 7 days a week at about 1,200 to 1,300 gallons per minute, and the upper part of that screen is completed in the formation, the same formation as the contamination. So that's what's known as the Pouillet formation. And in 2005, the laboratory, Steve McQuinn, published a hydrology report stating that as PM4 is pumped, the radius of influence or the drawdown can be measured at about 8,000 feet. So we're aware of this, we are monitoring it, and so this is a very high priority for the lab and for the Oversight Bureau. So far, we need more data, but so far the numbers are within our upper tolerance limit for background.
So are you saying that the pumping of PM4 could be influencing the migration of that plume?
I think so, in the Pouillet formation where the contamination is.
And what's that tributary? That's San I, right?
Yeah, so San Alfonso Pueblo, this is the boundary between Los Alamos and San Alfonso Pueblo. This is just the boundary between Los Alamos County and Santa Fe County. So we do have, and a question came up earlier just as a supplemental note, there is a perchlorate plume that is roughly on this portion of the laboratory. So wells R15, R50, so these also have chromium and perchlorate. But, you know, one working hypothesis is that the chromium that is detected at these wells, R15, that's about 12 micrograms per liter, and at R50, at about 100 micrograms per liter, that chromium and perchlorate could be sourced from Morton-Dad Canyon. Because the perchlorate, there was far more perchlorate released into Morton-Dad Canyon than Sandia Canyon. Okay. Now, let's look at some just back-of-the-envelope calculations on how fast this chromate is moving. Chromate, under the conditions of the regional aquifer, it transports relatively easily. So from the pumping test data that was conducted at R28, the range of values for the movement of the groundwater was from 73 to 164 feet per year. The ability for the rocks to remove some of the chromium, this is known as a retardation factor, that value is estimated at 1.5. That represents a lower, that's a lower value, stating that there's probably not much attenuation or attachment of the chromium onto the rock surfaces in the aquifer. If the retardation factor was 100, that would indicate there's strong attenuation. So what this retardation factor tells us, basically, it gives the relative movement of groundwater, the groundwater flow rate, to the movement of the contaminant. So the groundwater is predicted to move 1.5 times faster than the chromate is moving. So the rates of movement of chromium range from about 49 feet per year to about 109 feet per year, and the more likely ranges is 83 to 109. The laboratory in their 2012 report said this could even be higher, and so everybody's in agreement that the chromium is mobile in this part of the regional aquifer. Okay, so why is chromium mobile in the regional aquifer? There's other rocks like basalts where chromium can be attenuated. If you have a wetland environment with all this organic carbon, it gets reduced, chromium 6+ to chromium 3+. It's a wonderful system for remediation, the wetlands. Well, what we observed, this is a conceptual model of part of the regional aquifer beneath Mortgett Canyon. And when we consider an aquifer, we've got to look at the groundwater and we've got to look at the rocks that make up the aquifer, because the geochemistry that takes place is at that interface between the solids and the groundwater. So we know from extensive monitoring data that the pH in the regional aquifer ranges from about 7.5 to 8.5. The dissolved oxygen concentrations range from about 4 to 7 milligrams per liter. This indicates that the groundwater is moderately to strongly oxidizing. Okay, you can measure dissolved oxygen. Two key metals that are important in chromium transport are iron and manganese. If you have reduced iron in a system, iron 2+, that is a great reductant for chromate. That will really enhance converting chromate to chromium 3+. On the flip side of that, if you have manganese 4+, like desert varnish, the dark stained materials on some of the rocks, the chromium 3+ can oxidize and reduce the manganese 4+. But fortunately in our system, there's a lot more iron than there is manganese in the rocks. So the chromate, say like at R42, where we've measured up to 1,250 micrograms per liter, it's stable because there's dissolved oxygen. All the iron is oxidized. There's just no reductive capacity of the natural system. And if we looked at that, this represents some of the solid minerals, manganese dioxide, ferric hydroxide, that are known to occur in the aquifer. So under these conditions, there's just no reductive capacity of the solids, and so chromate is just stable as chromate. Okay. Now, if we had a system like in the basalts, and this is part of the good news, that the basalts have a lot of reduced iron, iron 2+. There's a lot of iron, magnesium, silicate minerals that make up those rocks. And so in a basalt, say, if we had like iron sulfide minerals such as pyrite, solid organic matter, then these phases, the iron 2+ phases, solid organic matter, have the ability to reduce the chromate to chromium 3+. And so we have evidence, geochemical evidence, that part of this is occurring above the water table in the basalts. And in the wetland, the San Diego Canyon wetland, and I've studied this extensively, over 99.9% of the chromium in that wetland is stable as trivalent chromium. So we want to keep that wetland wet, we want to keep it thriving, and that will be a very good remediation for the chromium that's in the upper part of Sandia Canyon. Okay, so we get this information from drilling wells, looking at the water chemistry, collecting core samples, looking at the mineralogy. Okay, now, a word on redox, a photograph on redox is worth more than 1,000,000 words that I just told you. Here is an example of a sedimentary formation where this is a redox interface between iron 3+, the brown staining, and iron 2+, where the iron has been leached out of the rock. Note the lizard for scale here. I didn't realize this till about after a year. When I took the photo, I go, oh, that was fortuitous. So, relating to chromium stability, iron is going to be key. If the iron is reduced iron, it can, iron 2+, it can reduce the chromate, and chromium 3+ will be stable. And if chromium 3+ precipitates from the groundwater, the equilibrium concentrations are on the order of about 3 micrograms per liter. So there's no issues with regulatory limits, and that's what I think for our background concentrations at the lab, it's probably controlled by the precipitation of a chromium hydroxide 3+ mineral. Now, if, say, at some point this sandstone was an aquifer, because to get this iron to precipitate out this iron oxide, this sandstone had to react with water. Now, if all this iron gets oxidized to iron 3+, prior to any contamination of the chromate, there's not going to be a reductant because the iron's already oxidized. So it's not going to do anything for reducing chromate. So these oxidation reduction reactions, and there have been great discussions. I've watched the YouTube presentations that in the geologic record we have excellent examples of redox. And this photograph shows a boundary between iron 3+ and iron 2+. Okay. All right. Now let's look at some trends of chromium concentrations over time. As the chromium has entered the regional aquifer, and it could have entered the regional aquifer beneath Morgan Canyon from 1980 to 1982, as the chromium spends more time in the regional aquifer, like at R28, it can approach what is known as steady state conditions. There are variations where there's increases and decreases in the chromium concentration, but overall, the trend of this is flat. There's not really an increase in chromium concentrations over time. So this indicates probably at R28 that typically has 400 micrograms per liter chromate. That chromium has been there a long time and is kind of equilibrated with the rocks in the groundwater. Okay, if we look at R50, that is south of R28, we see here an overall increasing trend. When the well was drilled in 2010, the concentrations were about 70 micrograms per liter, and now they're up over 100. And we see some valleys and peaks in this, but overall the concentration's increasing. To me, that indicates the plume is migrating. It's not stagnant. If you have a point in space and you have a contaminant moving through to that well, and the concentrations are increasing over time, that plume is migrating. Okay. Now, here's just two slides. This is for well R45 that is east of R28. When this well was drilled, the chromium concentrations were about 10 micrograms per liter in the upper stream that's closer to the water table, and about 3 micrograms per liter in the lower stream. But what we see here from 2009 to through 2012, the chromium concentrations have increased. And so what's significant about this screen here, screen A, is closer to the water table, maybe about 40 feet below the water table, and screen 2 might be 100 feet below the water table, that the concentrations are increasing in both streams. And so as this plume is migrating, it's displacing the native groundwater, and so now we're starting to see a vertical component to that. Okay, now our background, the mean is about 3.12. Our upper tolerance limit is about 5.2. Okay. All right. This slide shows we have great tracers from a geochemical perspective. A tracer is a chemical that will move at the same rate as the groundwater. So this shows a plot of 1/chloride versus sulfate. And sulfate, background chloride is about 2 milligrams per liter. So if background would plot over here at about 0.5, and then background sulfate is about 5 milligrams per liter. When we plot the 1 over the ratio of a tracer, we see a nice mixing curve here, okay? So this shows R42 and R28, and the sulfate concentrations at R42 range from about 60 to 75 milligrams per liter. Background's about 5. Okay, at R28, the sulfate ranges from about 38 to 55 milligrams per liter. So we can kind of track how this plume or plumes, how this is tracking through the system by looking at chloride and sulfate. And we see there is kind of a split. The triangles here, this is for R43, and then the squares here the diamonds here are for R50. And these two wells, R43 and R50, are near the fringe of the plume. And so where we see more chromium contamination, it relates to where we have higher sulfate concentrations. Okay. So we know groundwater mixing is occurring. The plume is migrating through the aquifer. It's displacing native groundwater, but it's also mixing with that water. And this just shows another example of mixing by looking at the ratios of sodium over sulfate and boron over chloride. Now sodium, there can be increasing concentrations of sodium from industrial discharges, from road salt. Sulfate can be added as neutralized sulfuric acid. Boron is associated with sewage effluent, and the chloride can be associated with sewage effluent as well. So on this, up here, this represents our background regional aquifer. And all these different wells that are shown can be mixing with native groundwater. They're contaminated, and so there can be a varying amount of mixing as this plume is migrating through the regional aquifer. Yes, sir.
What is the depth? Are all these wells at the same depth? What is the depth?
Depths.
I haven't seen anything that says
Yeah. The wells in the regional aquifer are usually 950 to maybe 1,100 foot depth. The wells above the regional water table, but in these perched intermediate zones that Danny Katzman has talked about, 500 to 700 feet depth. So there is a depth component with this. Okay. So how this information is useful if we're trying to figure out, well, if you had a well like R42, as we look at this, R42, R28, which are the most contaminated wells in the regional aquifer, and this intermediate well, Sandia Canyon Intermediate 2, these wells always tend to plot fairly close together, and that would imply that there was the same source of contamination affecting those wells. So we kind of use this as a forensic tool to sort out, could there have been more than one source? Could there have been more than one drip point where the contaminant is entering the regional water table? All right. Now, with that, what I'd like to do is focus on monitored natural attenuation. The EPA, other regulatory groups have realized that if there's certain biochemical, geochemical properties of the aquifer material, the solids, that could lead to a reduction in the concentration and volume of contaminated groundwater in a given aquifer. So with this, we'll just look at the inorganic. Here is a plan view map of a hypothetical plume, and this is the source. And it's migrating in this direction to the lower right. Now, if this was a contaminant that could undergo natural attenuation, the contaminant would attach to the mineral surfaces either through adsorption or precipitation, and ultimately there would be a decrease in the actual volume of the groundwater that was contaminated. There is always that contaminant present in the groundwater if it's not pumped out. Okay, so if we're going to look at natural attenuation, we would want to know, well, what's the mechanism causing the natural attenuation? Is this process effective to decreasing the contaminant concentrations to values less than the drinking water standard or the groundwater standard? So I think this is a viable process. It's not going to be applicable to all areas of the contamination at Los Alamos, but in some areas, such as in the basalts, it could have some applicability. Okay, so the EPA has developed criteria for evaluating this natural attenuation, and if there is natural attenuation, say of chromium in a groundwater aquifer system, we would expect decreasing concentrations of hexavalent chromium over time. We would expect a decrease in the volume of contaminated aquifer material over time. And we would hope for that there's abundance of, or a high reductive capacity of the aquifer material to reduce the chromium 6 plus to chromium 3 plus. And in our systems here, most likely that would be reduced iron 2 plus. Also, we would want to look at, say, if it was oxidizing, could the hexavalent chromium attach to the solid surfaces, and would they stick on there and not easily come off? So they attach to a surface, they're firmly attached, and over time they would rapidly be released back to the groundwater. And if minerals had precipitated out, if chromium 3 plus minerals precipitate out, we would hope that would be a very fast process. Now another aspect is too, these geochemical reactions that we hope to take place to remove chromium from groundwater, they occur at different rates. Some might be on the order of weeks, others might be on the order of decades to 100 to 1,000 years. And if the groundwater moves slow enough for those reactions to take place, then there's a good chance for this to happen. If the groundwater is just zipping through and it's moving faster relative to the rates of these reactions, there's not going to be much attenuation. Okay, and then we hope from a regulatory perspective that if this natural attenuation is occurring, that the end product would be, the total dissolved chromium would be less than 50 micrograms per liter. We'd all be happy if that was the case.
Okay. Speaking of be happy, Pat, it seems that the plume has breached the Sinai boundary. Are they happy about that? What have you heard from them?
Well, this is an important aspect. I think there's a very high probability it has passed R50, and San Ildefonso Pueblo is aware of that, and so I think that just needs to be sorted out. I think, and I hope that, both parties, everybody's interested in determining that question. Because we would want to know that if we're going to, the lab is starting to remediate the aquifer, and if it's this pump and treat method, you've got to know the nature and extent.
So are they happy with what's going on and that this almost is working at a fairly decent?
I guess I've been involved in one meeting with this, and I don't know if other meetings have taken place, so I don't have the most up-to-date information. So I can't answer that.
You kind of fit your plume to the information you had, but in reality, it could be a lot further down on Santa Alfonso than that indicated.
Right. Based on the increase in chromium concentrations at R50 and the mobility that we see there, it's a reasonable working hypothesis that it's migrated south of R50.
And with what you said, it doesn't seem like natural attenuation is occurring on the front lines of the plume.
Alex, that's a really good question, because initially it could, to a small scale, say like at that leading edge of the plume, if it was like 10 or 15 micrograms per liter, the rocks and minerals probably could react with that. But I think what's happening is that the chromium, the mass of chromium moving through is just saturating or overwhelming that system. And then the empirical evidence for that is given well like R50, you plot chromium concentrations versus time, and they increase.
They're increasing in one well?
They're increasing at R50 and then R43. That's more, R43 is in the Sandia Canyon, so that's and then some of the other wells like R44 that we just looked at, it's increasing at that location. Some of the wells like R15 that are further up the canyon, it kind of appears like it's steady state. So, initially there probably is some attenuation, but because of the mass that's moving through, the system just gets overwhelmed.
Hey, so Pat, this is great. I think you really have given us a lot of information. We're running a little behind schedule, so maybe we can go ahead and transition, spend about 5 minutes in question phase, and then Steve Venus will brief us out right before dinner.
Okay. If I could just show the summary conclusion.
Absolutely,
okay.
Absolutely.
Okay, so basically, from the empirical data, chromium 6+ is stable in the regional aquifer system, which is characterized by strongly oxidizing conditions with some of the key elements like iron, manganese, and dissolved oxygen. Based on some initial calculations, the chromium appears to be migrating nearly at the same rate as groundwater flow. There's some uncertainties about the mass, the nature and extent of contamination in the Beto zone, which overlies the regional water table in the regional aquifer. And this is based on R62 initially being drilled, thinking it was background, but now has between 100 and 200 micrograms per liter chromium, and then R50 that now has 100 micrograms per liter. I believe, based on a geochemical analysis of this, that natural attenuation is not an effective process for removing chromium below regulatory standards. And this is the key, that the successful remediation of chromium in the regional aquifer is going to be dependent on our understanding, and I emphasize the laboratory, the New Mexico Environment Department, the CAB, how well we understand the system. And the key components of that are the nature and extent of contamination. Secretary Flynn has emphasized this point at the last CAB meeting, and the geochemical, biochemical, and hydrologic characteristics. Thank you much, and sorry I overran.